Bismillah ar-Rahman ar-Rahim. We have an integral x from 0 to infinity log alpha squared plus x squared. Alpha is a positive real number. Then we have this ratio of hyperbolic signs. The argument in the denominator is pi x. The argument in the numerator is pi x times p over q. P and q are positive integers. P is strictly less than q. P and q have opposite parity, which means that p plus q is an odd integer. Let's start by investigating a couple of integrals that have this ratio of hyperbolic signs. A is a real number in the open interval between minus pi and pi. To obtain this integral, use the hyperbolic sign of theta is e to the theta minus e to the minus theta divided by 2. In the numerator, we get e to the ax minus e to the minus ax. Downstairs, we have e to the pi x minus e to the minus pi x. We can multiply upstairs and downstairs by e to the minus pi x. We get this e to the minus pi x in the numerator. The denominator becomes 1 minus e to the minus 2 pi x. If we have beta with a magnitude that is less than 1, 1 over 1 minus beta is 1 plus beta squared, and so on. We can apply this to 1 over 1 minus e to the minus 2 pi x and write this part as summation g from 0 to infinity e to the minus pi x to the power g. Then we have this e to the minus pi x. Together we get a summation g from 0 to infinity e to the minus pi x, and then we have 2g plus 1. We can multiply this exponential by these two guys. We get these two exponentials. In both, x is multiplied by something that is strictly positive. So when we integrate, we get a finite value. The smallest value of j is 0. Pi minus a is positive, and pi plus a is positive because the absolute value of a is strictly less than pi. Note that a can be complex, and these integrals have a finite value if the absolute value of the real part of a is strictly less than pi. When we integrate, we get 1 over this bracket minus 1 over that bracket, and we can combine them together. Our integral is summation g from 0 to infinity 2a divided by pi squared times 2g plus 1 squared minus a squared. This summation has a closed form. We call the product formula for cosine. Cosine beta is the product g from 0 to infinity 1 minus 4 beta squared over pi squared 2g plus 1 squared. Set beta equal to a over 2. Then take the natural logarithm of both sides. On the left-hand side, we get log cosine a over 2. The logarithm of the product is a sum of logarithms. 4 beta squared is equal to a squared. Differentiate both sides with respect to a. We get 1 over cosine a over 2. And then by the chain rule, the derivative of cosine is minus sine. And since we have a over 2, we also have 1/2. The derivative on the left-hand side is minus 1/2 the tangent of a over 2. On the right-hand side, we have 1 over this quantity here. Then by the chain rule, we get minus pi squared times 2g plus 1 squared in the denominator. Upstairs, we get 2a. Multiplying this part by that part, we get this summed here. Compare this with the result of our integration. It is exactly the same quantity, but with a minus sign. This means that this integral is equal to minus half times tan a over 2. That is 1 over 2 times tan a over 2. The result holds so long as the absolute value of the real part of a is strictly less than pi. Because we have this quantity here in the integral of interest, we will also be interested in having this ratio multiplied by cosine xz, and then integrating from 0 to infinity. Z here is a real parameter. Cosine xz is the hyperbolic cosine of ixz. The product of hyperbolic sine and hyperbolic cosine can be written as 1/2 the sum of two hyperbolic sines. The argument of the first is the sum, and the argument of the second is the difference. We can now employ our previous result, provided that a is real and is in the open interval between minus pi and pi. Because of this 1/2, we get 1/4 tan a plus iz over 2 plus 1/4 tan a minus iz over 2. In this case, a is real, z is real. As we can see that these arguments are the complex conjugate of one another, so we can multiply by 2 and take the real part. What is the real part of the tangent of a plus iz over 2? That's the real part of sine over cosine. We can apply the rules for the sum and the relations between sine and cosine and their hyperbolic versions. Multiply the numerator and the denominator by the complex conjugate of the denominator. Downstairs, we get cosine squared a over 2 times the hyperbolic cosine squared of z over 2 plus sine squared of a over 2 times the hyperbolic sine squared of z over 2. In the numerator, we can focus on the real part, which is obtained when we multiply these two terms minus the product of these two terms. When we do this, we have sine a over 2 cosine a over 2 as a common factor. Then we have this difference, which is 1. If we multiply by 2 and divide by 2, we have sine A in the numerator. The outside factor becomes 1/4. And in the denominator, we can also change the sine and the hyperbolic sign into cosine and hyperbolic cosine. If we multiply these two brackets, we get -1 plus cosine squared A over 2 plus hyperbolic cosine squared of Z over 2 minus cosine squared times the hyperbolic cosine squared. This fourth term is cancelled with this part here. We are left with 3 terms. Split this 4 into 2 times 2 and multiply the terms in the denominator by 2. We can think of this -2 as -1 minus 1. 2 cosine squared A over 2 minus 1. That's cosine A. And 2 hyperbolic cosine squared of Z over 2 minus 1. That's the hyperbolic cosine of Z. This integral here is 1/2 sine A over cosine A plus the hyperbolic cosine of Z. Z is real, A is between minus pi and pi, and this is consistent with our integral of interest. Note that this hyperbolic sign is applied to pi P over Q, and we have this constraint here that P is less than Q. X is multiplied by a positive real number that is strictly less than pi. On the next page, we turn our focus to this part here. We will try to write down an integral representation for the logarithm of 𝛼² plus x². Alpha is strictly positive, V is strictly positive. This is a standard integral, an exponential multiplied by sine, and this can be solved by doing integration by parts twice. The result that we get is the integral with respect to z from 0 to infinity of e to the minus alpha z sine vz is v over 𝛼² plus v². Now integrate both sides over v from 0 to x. On the right hand side, the antiderivative is 1/2 the logarithm of 𝛼² plus v². Then we use our limits of integration from 0 to x. So we get 1/2 log 𝛼² plus x² minus 1/2 log 𝛼². This is minus log alpha. On the left hand side, let's assume that we can interchange the order of integration. Let's do first the integration with respect to v. We have a sine function. The antiderivative is minus cosine. When we use our limits of integration, we get 1 minus cosine xz divided by z. We are left with this integral over z. Move this term to the other side and multiply by 2. Log 𝛼² plus x² is double this integral plus 2 times log alpha. Log alpha can be represented using this integral from 0 to infinity, e to the minus z minus e to the minus alpha z over z. One way to see this is to write the integrand as the integral over t from 1 to alpha of e to the minus zt. If we do this integration, we get the z in the denominator, and then we will have e to the minus z times 1 minus e to the minus z times alpha. Assume we can interchange the order of integration. The inner integral now is with respect to z. It is equal to 1 over t, and the integral of 1 over t is log t. Using the limits of integration, we get log alpha minus log 1, which is log alpha. This log alpha here can be represented using this integral. Log 𝛼² plus x² is given by the sum of these two integrals. We can combine them. Note that the integrand here has e to the minus alpha z over z. The integrand there, it has minus e to the minus alpha z over z. These two terms go away, and we are left with these two terms, e to the minus z over z minus e to the minus alpha z cosine xz divided by z. And this is the integral representation that we need for log 𝛼² plus x². Recall that this is our integral of interest. Now we have 3 results. On the previous page, we obtained this integral and that integral. Now we have this representation for the logarithm. Let's use it. Replace the logarithm of 𝛼² plus x² in the integral of interest by this integration here. As usual, assume that we can interchange the order of integration. If we do the integration first with respect to the variable x, we obtain the two integrals that we have done earlier. The first integral gives us 1/2 the tangent of pi p over 2q. The other integral gives us 1/2 sine pi p over q, and in the denominator we have cosine of pi p over q plus the hyperbolic cosine of z. The 1/2 factors disappear because we have this 2 here. The integral of interest is now written in this form. Let's do change of variables. U is equal to e to the minus z, which means that z is minus log u. dz is minus du over u. When z is 0, u is 1. When z tends to infinity, u tends to 0. Z in the denominator becomes minus log u. E to the minus z is u. E to the minus alpha z is u to the power alpha. This term here is 1/2 e to the z plus 1/2 e to the minus z. This is 1 over 2u plus u over 2. Multiplying the denominator here by 2u, we get u squared plus 2u cosine by p over q plus 1. And we get this 2 upstairs. This is another form for the integral of interest. Note that our integration depends on alpha and on the two positive integers p and q. But let's emphasize the dependence on alpha and define this integral as omega of alpha. Because we have this minus log u in the denominator, if we differentiate under the integral sign with respect to alpha, we get log u in the numerator, which will cancel this term here. This is exactly what we do. We compute the derivative of omega with respect to alpha. The limits of integration do not depend on alpha. This term does not depend on alpha. And from here, we get 2u to the power alpha times the natural logarithm of u. We need now to evaluate this integral. Then we go back to omega of alpha. We can write the denominator as the magnitude squared of this complex quantity, 1 minus e to the I pi p over q plus 1 times u. And this is 1 plus e to the I pi p over q times u. What we do is that we take the magnitude squared or multiply by the complex conjugate. 1 times 1 is 1. This term times that term gives u squared. And then we have u times the sum of these two exponentials, which is 2 times cosine pi p over q. 1 over this quantity is the summation k from 0 to infinity. And then we take this term, raise it to the power k. Note that this is valid here because u is between 0 and 1. But we have the magnitude squared. So we need to take this sum and multiply by the complex conjugate. We get a double sum, e to the I pi p over q plus 1, k minus m, this minus because of the complex conjugate. Then we have u to the k plus m. The next step is to rewrite this double sum as a single sum, summation n from 0 to infinity, cn u to the power n. We equate the coefficients of u to the n on both sides. So cn is this double sum of those exponentials with the constraint that k plus m is equal to n. K and m are non-negative, and their sum is equal to n. The maximum possible value of each is n. We can use this constraint to rewrite the double sum as a single sum, k from 0 to n, e to the I pi p over q plus 1, and then we have k minus m. M is replaced by n minus k. This is the coefficient cn, which is this exponential times a finite geometric series. With n plus 1 terms, the numerator can be written as the difference between these two exponentials and this common factor. Also, we can rewrite the denominator as the difference between these two exponentials and this common factor. Those three exponentials, when multiplied, give us 1. Then we have minus 2i sine pi times n plus 1 times p over q plus 1. Downstairs, we also get minus 2i sine pi p over q plus 1. We can simplify the result by using the fact that sine theta plus pi times an integer, say v, is equal to minus 1 to the power v times sine theta. 1 over this magnitude squared is now given by summation n from 0 to infinity. The coefficients cn times u to the n du. We do term by term integration with respect to u. We get 1 over n plus alpha plus 1. Now we use the following trick. We rewrite this single sum as a double sum with two indices k and m. Specifically, we write n as k plus mq. Q is this positive integer. K is an integer that takes values from the set 0, 1, 2 all the way to q minus 1. M is a non-negative integer. Note that when m is equal to 0, k plus mq is from 0 to q minus 1. When m is equal to 1, k plus mq is from q to 2q minus 1. When m is equal to 2, k plus mq is from 2q to 3q minus 1, and so on. This may seem as if we are complicating things, but we will be able to rewrite our result in terms of the Digamma function. We rewrite the single sum as a double sum. Every appearance of n is replaced by k plus mq. When we do this, we get the sign of pi p over q times k plus 1 plus pi mp. This is the sign of pi p over q times k plus 1 times minus 1 to the power mp. We have minus 1 to the k plus mq. Now we have plus mp. This is minus 1 to the k times minus 1 to the p plus q, all to the power m. In our integral of interest, p and q have opposite parity. Their sum is odd, so this is minus 1. This term here is minus 1 to the power k plus m. Let's change k to k minus 1. Now k is from 1 to q. Every appearance of k is replaced by k minus 1. This becomes k, this becomes k, and this becomes k minus 1. Note that if k is equal to q, we have sine pi p, which is equal to 0, because p is an integer, so we can stop the sum at q minus 1. What we have is 2 summation k from 1 to q minus 1, minus 1 to the power k minus 1, this sign here. Then we have the sum with respect to m, summation m from 0 to infinity, minus 1 to the power m, 1 over k plus mq plus alpha. Let's rewrite this sum as even and odd index terms. We get the difference between these two fractions. In one of them, m is replaced by 2m, and in the other, m is replaced by 2m plus 1. The goal here is to represent our result in terms of the Digamma function, 𝛼 of z, which is the logarithmic derivative of the gamma function. 𝛼 of z is minus small gamma, the Euler-Mascheroni constant, plus summation j from 0 to infinity, 1 over j plus 1 minus 1 over j plus z. In this series representation of the Digamma function, we have this summation from 0 to infinity. Then we have a fraction 1 over the summation index plus z, and this z is the argument of the Digamma function. We have here a summation m from 0 to infinity. To prepare the ground for introducing the Digamma function, we take 2q as a common factor from each denominator so that we have m alone. When we do this, we get m plus k plus alpha over 2q in this fraction, and m plus k plus alpha plus q over 2q in the other fraction. We add and subtract small gamma. We also add and subtract this term here. So we match exactly the series representation of the Digamma function. Minus small gamma plus this sum here is 𝛼 of k plus alpha plus q over 2q. Then we have a minus sign, and this part here is 𝛼 of k plus alpha over 2q. This is our integral of interest. We rewrote it in this way. This is the function omega of alpha. We differentiated once with respect to alpha. We got that integral, which is equal to a finite sum with q minus 1 terms. The summand includes this difference of Digamma functions, which is very good. The Digamma function is the logarithmic derivative of the gamma function, which means that we can obtain the antiderivative and get omega of alpha. The antiderivative is 2q log of gamma of k plus alpha plus q over 2q minus log gamma of k plus alpha over 2q. We can write this as the logarithm of a ratio of gamma functions. The issue now is to obtain the constant of integration. It turns out that this is not as straightforward as one hopes for. If we compute the difference between two omegas, this constant goes away. We can use this integral representation and write down omega 2 minus omega 1. When we do this, this part of the integrand goes away, and we have this integral representation. If we do omega 1 minus omega 0, we get this integral. If we subtract, we have u minus u squared from here, minus 1 minus u from there. This is 2u minus 1 minus u squared. This integral represents omega of 2 plus omega of 0 minus double omega of 1. Working with differences eliminates the integration constant c, but we need to obtain it. What will help us achieve this goal is omega of 1. To study omega of 1, set this alpha equal to 1, and then combine these two terms. We have tan pi p over 2q multiplied by the denominator. Tan pi p over 2q is multiplied by u squared plus 1 plus 2u times this cosine, which can be written as 2 cosine squared pi p over 2q minus 1. Then we have minus 2u sine pi p over q, which is written as 2 sine pi p over 2q cosine pi p over 2q. We have u squared plus 1 minus 2u multiplied by this tangent. Then we have 2u times 2. The tangent is sine pi p over 2q over cosine pi p over 2q. The product of tangent and cosine squared is sine pi p over 2q times cosine pi p over 2q. This is exactly that term, but with an opposite sign. These two guys go away, and we are left with this part here. Take the tangent outside the integral. Multiply and divide by sine pi p over q. If we compare this integral with that integral, they are exactly the same, except this factor of 2. In other words, omega 1 is equal to this outside factor. And this integral here is this quantity divided by 2. Omega of 1 is minus tan pi p over 2q over sine pi p over q. Then we have omega of 2 plus omega of 0 minus 2 times omega of 1, all divided by 2. We can use this relation to write down omega of 2 plus omega of 0 in terms of omega of 1. After doing this, we can write omega of 2 plus omega of 0 minus 2 times omega of 1 as a function of omega of 1. Specifically, this quantity is omega of 1 times minus 2 divided by this ratio here. This is not pointless. The idea is that this quantity here came from differences. And so we don't have the integration constant c on this side. But omega of 1, using this general formula for omega of alpha, has c. We can use this relation here to obtain c. Our integral of interest is exactly omega of alpha. The final result depends on the real positive number alpha and the integers p and q. The only remaining issue is that we need to obtain c as a function of p and q. On the previous page, we found out that this quantity here is omega of 1 times this factor. We can take this sign upstairs. This factor is minus 2 times the sign, which can be written as 2 sine pi p over 2q cosine pi p over 2q. We have minus 4 sine times cosine divided by the tangent of pi p over 2q. All in all, we get minus 4 cosine squared pi p over 2q. This bracket here is omega of 1, written explicitly with the integration constant c. We can also use the general formula for omega of alpha to write down this quantity, and we will not have c because we are talking about differences. When we write down omega of 2, omega of 1, and omega of 0, the arguments of the gamma functions depend on alpha. So this alpha is replaced by 2 when we talk about omega of 2, by 1 when we talk about omega of 1, and by 0 if we talk about omega of 0. To facilitate the process of obtaining c, we can try to write down every gamma function with these arguments, k plus 1 plus q over 2q and k plus 1 over 2q. How can we do something like this? If we write down omega of 2 minus omega of 1, then we get two sums. In this sum, we can replace k by k minus 1. When we do so, we get our gamma functions looking exactly like this. There will be a shift in the index. The index is from 2 to q, while in this summation, the index is from 1 to q minus 1. We can separate the term corresponding to k equal to q from this sum, and the term corresponding to k equal to 1 from that sum. We get those isolated terms. Then we have a summation, k from 2 to q minus 1. And in this summation, the gamma functions appear exactly like this. The same idea can be applied when we examine omega of 1 minus omega of 0. We have this sum, which looks fine, and then that sum. We want the gamma functions to look like this. We can replace k by k plus 1 in this summation. The index of summation is shifted. No problem, we will have those terms and a summation with the gamma functions looking as desired. Now we compute the difference, and the difference looks like this. Because we have adjusted the gamma functions to have the same argument, we get different arguments for the sine function. We have sine pi p over q k plus 1 plus sine pi p over q k minus 1. These two signs can be combined as 2 sine pi p over q k and then cosine pi p over q. We can take 2 times the sine as a common factor. We get a bracket with 1 plus cosine pi p over q, and this bracket is 2 times the cosine squared of pi p over 2q. This quantity here is this bracket multiplied by minus 4 cosine squared pi p over 2q. Now we equate these two quantities. Very nice cancellations will happen. Note that this term here is exactly like that term. However, the sum here is from 1 to q minus 1. Here it's from 2 to q minus 2. So from here we need to separate the term corresponding to k equal to 1 and to k equal to q minus 1. And then we can eliminate the sum from k equal to 2 to k equal to q minus 2. The extra terms are eliminated with one exception, this quantity here. Dividing both sides by minus 4 times cosine squared, we get that c is equal to minus 2 over minus 4, that's 1/2. And then we have this sign, which can be written as 2 sine pi p over 2q cosine pi p over 2q. And then we have this cosine squared. 2 goes away with 2, cosine with the square, and we end up with the tangent of pi p over 2q multiplied by the natural logarithm of 2q. This is the constant of integration. Our integral of interest is equal to this quantity here. As a special case, if p is equal to 1 and q is equal to 2, the integral from 0 to infinity, the hyperbolic sign of pi over 2x divided by the hyperbolic sign of pi x. Note that this ratio is 1 over 2 times the hyperbolic cosine of pi x over 2. If this ratio is multiplied by log alpha squared plus x squared dx, we get tan pi over 4, that's 1, log 4, because q is equal to 2, we just have one term from this summation here, corresponding to k equal to 1. We get 2. When k is 1, this is 1. When k is 1, we have sine pi over 2, which is 1. Then we get the logarithm of gamma. K is 1 and q is equal to 2. We have alpha plus 3 over 4 divided by gamma alpha plus 1 over 4. Whenever this formula is applied, please keep in mind that we need to satisfy those constraints here. P plus q must be odd and b is strictly less than q. If p plus q is even, we get something that very much looks like this, but it's a different formula. And the proof is almost the same.